So as a reminder, given quantities A and B, a linear combination of A and B, here A and B are just integers, or they can be real numbers, or they can be elements of a vector space, if you know what that is, or they can be anything we want. But given two quantities A and B, a linear combination of A and B is a quantity of the form, so is a quantity of the form AX plus BY. So the reason why this is relevant for us now is that I want to talk about what's called Bézout's little theorem. Bézout is a mathematician from the 19th century. He has a very important theorem in algebraic geometry named after him, but this is called Bézout's little theorem. And what it says is that if A and B are positive integers, so if A and B are positive integers, then the greatest common divisor of A and B is the smallest positive integer. So it's the least positive integer that can be written as a linear combination of A and B. Okay, so that can be written as a linear combination. So it's a linear combination of A and B. I am not going to prove this completely. I'll leave the details to you. But a few things that I want to say. If we take the GCD of A and B and we write it as a linear combination of A and B, here, remember, everything are integers. So our X and Y and B and A are integers. So if the GCD of A and B is written in this form, AX plus BY, then X and Y are called Bézout coefficients. So they're called Bézout coefficients of A and B. Bézout coefficients are not unique. Okay, in fact, there's infinitely many, but if we can write the GCD as a linear combination of A and B, then those constants X and Y, those integers X and Y, are called Bézout coefficients. I will talk about how to actually find Bézout coefficients in general, because this is going to be a process that will lead us to solving congruences, which is where we're going next. Before we do that, I want to do a little bit of an example. And so this is not going to be a proof, but this is at least going to hint how you could prove this in general. So let's write, let's say 7 and 11 as a linear combination. I'm saying this backwards. Let's write the GCD of 7 and 11 as a linear combination of 7 and 11. Okay, clearly 7 and 11 both being primes, their GCD is 1. But what I want to do is I want to use the Euclidean algorithm anyways, because we're going to kind of work backwards from the Euclidean algorithm. And so what we're going to do is we're going to say, well, 11 is 7 goes in one time with remainder 4. 4 goes into 7 one time with remainder 3. 3 goes into 4 one time with remainder 1. And then finally, 1 goes into 3 times. Okay, and so our last non-zero GCD, our last non-zero remainder is the GCD. So of course the GCD of 7 and 11 is 1, which we knew 2 minutes ago. But what I want to do is I want to actually go through this process backwards and kind of unfold this and think about how we can write 1 as a linear combination of 11 and 7. I picked 11 and 7 because maybe you can already see how we're going to write it. But we'll talk about how we can build this from scratch, more or less. So what I'm going to do is I'm going to ignore this last equation. It's not very useful. And so we can just pretend that that's not there. And I'm going to take the second to last part, which is 4 equals 3 plus 1. And I'm going to solve it for the GCD, because remember what we want to do is we want to write the GCD is a linear combination of 7 and 11. And we're going to work backwards. So we don't need this bottom equation. We just use this second equation from the bottom. And what we're going to do next is we're going to kind of successively walk backwards through these remainders. So 1, 3, and 4. So the next thing that we're going to do is we're going to replace 3 with, well, if we solve this equation for 3, we will get 7 minus 4. So this implies that we're going to get, so 3 we can think of as 7 minus 4. And now the trick is that we want to write 1 as a linear combination of our dividend and our divisor, 7 and 4. So we want to write 1 is, let's see, if we distribute this, we're going to get 2 4s and 1 7. And of course, 2 times 4 is 8, minus 7 is 1, so that all checks out. So this is writing 1 as a linear combination of 4 and 7. We're going to do this again. So we used 3 is 7 minus 4. We're going to do this one more step. We're going to write 4 is 11 minus 7. So I'm going to replace the 4 here with 11 minus 7. And then we're going to keep the 7s and the 11s together. So we're going to write that 1 is, let's see, we have 2 11s. And we have, if we were to distribute this, we get minus 2 times 7 minus 7 will be minus 3 times 7. And so here we go. We have 1 is 2 times 11 minus 3 times 7. This process of working backwards through the Euclidean algorithm will always work. And that shows that the GCD of two integers can always lead you to a representation of a linear combination. In other words, this will always produce Bézout coefficients, this algorithm. Now, to show that the GCD is the smallest positive integer with that property is a little bit tricky. But what I want to do is to convince you of that. Let's say that we had the GCD of, let's say 12 and, let's make something up good, let's say 33. Okay, now clearly the GCD is going to be, this is 3 times 4, this is 3 times 11, so the GCD will be 3. Again, I picked numbers that are small enough where this should be pretty self-explanatory. What I want to do is I want to argue why you cannot write 2 or 1 as a linear combination of 12 and 33. Suppose that you could. Say you could write 2 as a linear combination. In other words, suppose that there were integers x and y, one of which would have to be positive, one of which would have to be negative, but suppose there were integers x and y, where you could write 2 is equal to 12x plus 33y. What's the problem with that? Well, the problem with that is that the right side is a multiple of 3, and the left side is not. And we know by the fundamental theorem of arithmetic that prime factorization is unique. So there's only one way to write any number as a product of primes. So you can't have a different prime factorization. You can't have 2 prime factorizations for the same number, right? So this would imply that 2 is a multiple of 3, right, which we know isn't going to work. And likewise, 1 wouldn't work there either. Okay, so again, not a rigorous proof, but at least an idea of why you cannot write 1 or 2 as a linear combination of 12 and 33. So in general, if the GCD of A and B is D, then D you can write as a linear combination of A and B. And then any positive integer less than D you cannot, because the right side would be a multiple of D, the left side would be something smaller that's not a multiple of D. Okay, and so you have to be a little bit careful to make that argument rigorous, but you can, and I will leave that to you.